This is a new colloquium of the series Postdoc on the Spot. So today it's a pleasure to have Pedro Pasquini. Pedro Pasquini was a postdoc here, then he moved for 3 years to Shanghai, and now he's in Tokyo. And today he's going to talk about neutrinos as a portal to new physics. Thank you very much.
Yeah, thank you. Yeah, so I'm going to talk about neutrinos today. You can stop me and ask questions when you have some questions. Thank you for the introduction. So I would like to start with a famous letter from Pauli. The letter is in German. I will show the translation in a second. But first I want to mention that it's been 94 years ago when Pauli wrote the letter that proposed the neutrinos. At that time, he called it neutron. Later, people changed it to neutrinos. And first, he talked about radioactive ladies and gentlemen, so he liked to do a little bit of jokes. There are many jokes in this letter, but there are many serious things that he was trying to discuss. The first of them is that he was discussing these wrong statistics of N and lithium here, and also the continuous beta spectrum. They have that problem that beta spectrum, they will detect the proton and the electron, which should be a single energy in the spectrum, but they actually observe this as a continuous spectrum. And they were thinking about how to solve that problem, and they were actually desperate to solve that, and then Pauli proposed this solution or remedy to save what he called statistics and conservation of energy. So they were ready to give up on conservation of energy to solve that. And then he proposed this particle that we call today neutrinos. And at that time, it was very hard for him to even think about publishing this idea because it's very unlikely to find that particle because the neutrinos don't interact too much. So it would be very hard to find experimental evidence of the neutrinos. Basically, the interaction that he thought at that time, it was 10 times smaller than gamma ray. Today we know that it's much, much smaller than that. And actually took 25 years from the proposal of the neutrino to actually detect the first neutrinos. So it was really difficult, but the idea was there, and people took seriously after he proposed that and in a letter. And the status of the neutrino physics today is completely different from that. I want to emphasize. These are the logos of some neutrino experiments. There are many more experiments. And here are the values that people are investing on the neutrino experiments. So for example, Dune, around 1.5 billion. Maybe these numbers are a little bit outdated, but the order of magnitude is around that. And if you sum all these numbers, just for these experiments, we get around $3 billion. And I'm not putting other numbers here. And there are many more experiments. So there are a lot of money in the neutrino sector, neutrino physics, experimentally, and even theoretical people are working a lot on neutrinos. So yeah, there are many more experiments than those ones. So what I want to convey and main takeaway of this talk is how and why neutrinos come from this shame scenario where Pauli didn't want to publish the idea to a global investment and many people discussing and talking about neutrinos. And of course, what kind of physics we can do with that, especially beyond standard model physics. The first question is the how. Well, how it's easy to explain a little bit. Neutrinos are a Nobel-producing machine. The discovery of the muon neutrino earned a Nobel Prize to these guys. The first detection of the neutrino also won a Nobel Prize. Funnily, muon neutrinos got a Nobel Prize before the first detection of the neutrino. Also, cosmic neutrino detection won a Nobel Prize. Very recently, sorry? Right, yeah. And then they, Lederman, Schwarz, and Steinberg proved that the first detected neutrino is different from this one, so they figured out it's a muon neutrino, which is a different neutrino, yeah. So very recently, there was a Nobel Prize from Kajita and McDonald related to neutrino oscillations. I will talk about that a little bit more later. And if I stretch a little bit, we can think about Young and Lee experiment, also some kind of relation to neutrino, since it's weak interactions, neutrinos left-handed, etc. So there are many Nobels related to neutrino in some way. But not only Nobel Prizes, but neutrinos are very important in many areas of physics and theoretical physics. First, it's one of the most abundant particles in the universe. The sun produces many, many neutrinos. Actually, there are 100 trillions of neutrinos passing through you right now per second. Those are electron neutrinos. Actually, there's a cosmic neutrino background. Of course, this image is not the cosmic neutrino background because we couldn't measure it yet. But there's roughly 700 million neutrinos per proton in the universe, so there's a lot of neutrinos around there from the C nu B. And actually, you that is listening to this talk is producing antineutrinos from decay, for example, kaon decay, and a rough estimate gives 10 million neutrinos that you are emitting through this talk. So a lot of neutrinos coming from you too. There's also, neutrinos are also an important part of nuclear reactions. There are many nuclear reactions mainly discussing, related to decays that are important for neutrinos. So the reactor that we use for generating energy have a reaction that related to neutrinos. The sun producing energy also related to neutrinos. The PET scan that we use in medicine also reactions related to neutrinos. Neutrinos can be used to study many things around us that is very hard to study in other ways. Earth, sun, supernova, everything emits neutrinos, and we can use neutrinos to observe the interior of these objects. For example, this is the photo of the sun obtained from Super Kamiokande using only neutrinos, which is, I think, very interesting. Also, supernova explosions, probably some theory says that supernovas can explode exactly because neutrinos, when they are produced during the collapse, so electrons, because of the pressure, electrons will fuse with protons producing neutrons, the proton-neutron star, and since neutrinos don't interact too much, eventually they can escape the supernova, and then they take 99% of supernova energy. So the supernova, very bright that we see in the sky, is actually 1% of the energy of the supernova. The other 99% goes to neutrinos. So there are a lot of neutrinos reaching us. And actually, multi-messenger astronomy can be very useful with neutrinos because during the burst of the supernova, neutrinos will be emitted, and we, in principle, can detect these neutrinos. And neutrinos will arrive faster than light. So if we are lucky enough, we can measure those neutrinos and point the telescope and observe the supernova before it explodes, or in the light spectrum. Actually, neutrinos have a more practical use, which is monitoring nuclear reactors and people doing tests of atomic bombs. This is a plot from this paper here that they show that depending on the detector that you use, you can build a detector that is small enough that you can go around Earth with the detector and detect the neutrinos, and they predict the number of events depending on where you are. So, for example, Brazil has the Angra reactors, then you can measure the neutrinos here. Around Europe, more neutrinos, United States, etc. Then you can monitor if people are using nuclear reactors and are not telling us that they are using, or tests of atomic bombs also can be used, can be monitored using neutrinos. Of course, neutrinos are crucial in cosmology. This is a very brief history of the universe that I would just point out the neutrino role. So we start with the plasma in the early universe, and then the cosmic neutrino background is created around 1 second. Around the CNB formation, neutrinos are 10% of energy density of the universe, so even there it has a very important role. It also has an important role in the structure formation, where we can infer the neutrino mass, or try to constrain the neutrino mass bounds, to constrain the neutrino mass. So neutrinos have a very important role. Maybe they are related to dark matter somehow. So neutrinos is an important part of cosmology as well. But what I'm going to talk about this lecture here is about this fact here that neutrinos technically are the first laboratory evidence of new physics that we have recently, and it might be a portal to beyond standard model physics. And why I'm saying that this is the first laboratory beyond the standard model physics that we have is because neutrinos oscillate, and that's the Nobel Prize awarded in 2015 that I mentioned before. Supercamacon and SNO detected these neutrino oscillations, and actually it's easier to see that neutrinos do oscillate from this Cameland plot here, which is roughly the number of neutrinos in the y-axis, and this L over E, so the distance traveled by neutrinos, and the energy of the neutrino. And we can clearly see from the data points, the black points, that there is an oscillation in the neutrino number, the number of neutrinos. And how we understand that today is that there is a probability of oscillation of the neutrinos, which looks like this approximation by two neutrinos. So there's some mixing angle that mix the two neutrinos, and there's this phase, so L over E here, L over E, and this phase is proportional to the mass square difference of the neutrinos. So if neutrino oscillates, then neutrinos have mass, and at least one of them, and they are different. This means that one of them, at least one neutrino mass is different from zero. And this is already, at least I'm calling here, beyond standard model, so technically. So there's an anecdote. I'm not sure how truthful it is, but people say that there was someone giving a talk, and Steven Weinberg was in the audience, and then the person was talking about the neutrino mass, etc. And then the person asked Steven Weinberg, do you think neutrino mass is in the standard model or not? And then Steven Weinberg said, neutrino mass are not in my standard model. Because when the standard model was constructed, people didn't think neutrinos have mass. They have no reason for that. And we discovered neutrino mass much later than that. And you could think, why not just giving neutrino mass through the usual Higgs mechanism? For example, we have the usual Yukawa coupling for charged leptons. We could simply add another interaction here, put this Y very small, and then add some right-handed neutrino, which is a singlet. Okay, we can do that. We can give neutrino mass like that. But if this is a singlet, we could also add this term here, and nothing would violate in terms of symmetry. And then if we add this term, then we get the Majorana neutrino. If we only have this term, we have a direct neutrino. So there are many possibilities on how to generate neutrino mass. So it's not really trivial to say which one is the one that we have to choose. So that's why people don't take neutrino mass as a standard model characteristic. And there's another reason to think that neutrino mass mechanism is different from the Higgs mechanism. I have plotted here the mass scale of the particles of the standard model, and we can clearly see that the standard model particles' masses are very different from the neutrino masses. Look, this is a log scale. There's a very big gap here in the neutrino masses. So maybe there is something there that is different from the Higgs mechanism. Not confirmed yet, but maybe there is. But now, what do we know about neutrinos in general? I will go back again to the Pauli letter and just point out that he already knew that neutrinos should be electrically neutral, spin 1/2, so it's a fermion. And I also want to point out that neutrinos, he proposed that neutrinos could have a magnetic dipole momentum. I will go back to that later, so that's why I brought up this letter again. But we know a bit more than that today. We know that there are at least 3 neutrinos. We call them nu1, nu2, nu3 if they are in the mass basis, or we call them nu e, nu mu, and nu tau if they are in the flavor base. So there are 2 bases that we can describe the neutrinos. We also know that these neutrinos can have mass, and their masses are all different from each other. One of them could be 0, but the other 2 are definitely not 0. And we also know that the sum of the neutrino masses should be smaller than 0.2 electron, roughly 0.2 electron volts. We know about the interactions of the neutrino related to the standard model. So neutrinos are collected in the SU2 doublet with the charged leptons. We know that the mass basis and the flavor basis are different. And this means that there is some mixing matrix that relates the mass basis with the flavor basis. And what this means in practice, for example, if the pion decays and produces an anti-muon, then by definition, this neutrino is the muon neutrino. And this means that it is a combination, a coherent combination of the mass neutrinos nu1, nu2, and nu3. And the wave of this combination is this mixing matrix here. So what's being emitted is this combination and not the mass neutrinos, for example. And we know, we parameterize this mixing matrix with the mixing angles. So we have the mixing angle θ1, 2, θ13, θ23, like Euler rotation matrix. And we have this CP violation phase here in the usual mixing matrix that we call PMNS matrix. And we actually have measured all these mixing angles and mass differences. So the mass difference between 2, 1 squared is 7.4 10 to the minus 5. We measure the 3, 1, the absolute value of this parameter here, 2 times 10 to the minus 3. So observe here that there are some hierarchy already in the masses of the neutrinos, which we would like to explain why this difference here. We have actually measured the mixing angles. So θ12 is around 35 degrees, θ23 is around 45 degrees, and θ13 is 9 degrees. And if these values didn't surprise you, perhaps it should, because the CKA matrix, which is conceptually similar to neutrino mixing matrix, the angles are much smaller, so they are very close to unit or small mixing angles. And we would like to explain why these mixing angles are different from the CKA matrix, so different compared to the PMNS and CKA matrix. But it's exciting, actually, that there are many questions. So this is one question. There are many questions that we would like to answer from neutrino oscillations. One of them is, are there more neutrinos? Especially, are there sterile neutrinos? Here? No, these angles are large. Yeah. The small is the CKM matrix angles here. So we know about neutrino masses. We would like to know about neutrino masses a little bit more. So we would like to know what's the neutrino mass scale, so what's the mass of the lightest neutrino. We only know the mass differences. And we actually don't know what's the sign of this mass difference here. So what this means, it means that we don't know if the M3 neutrino is more massive than M1, or if the M1 neutrino is more massive than M3. We don't know what exactly generates the neutrino mass, and we don't know what's the nature of the neutrino, if it's Dirac or Majorana. We don't know many things about the neutrino mixing parameters. So for example, we still haven't measured the delta CP phase. Actually, there are some new measurements from T2K and NOVA on the delta CP, and we can see clearly that the two regions of the parametric space, so the blue region is the NOVA, and the black contour here is the T2K. And if we take these experiments individually, they don't match with each other around 2 sigma if you do the calculation. So there may be some tension there in the data. Of course, we need more statistics, but maybe there's something there that we will observe in the future. We don't know the octant of the θ23. For example, if it's larger than 0.5, the sine square here, larger than 0.5 or smaller than that, or if it's exactly 0.5. That is also interesting for some models. We don't know if U is really unitary. It's really hard to probe the unitarity of this U matrix. I will talk about more about that later. And there are many things that we don't know about neutrino interactions. So the cross-section of the neutrino is actually hard to calculate, especially with neutrino and nucleons, because then we have QCD effects that for the nucleons, and then it's really hard. It's an open problem that will be necessary to solve in order to perform the future neutrino oscillation experiments. And we don't know if there are beyond standard model interactions related to neutrinos. So if there are many open questions on neutrinos, how can we use neutrinos to search for new physics? I will talk about these 3 options here. There are many more. But I will discuss these 3, which is oscillation, scattering, and atomic transitions. So the first one is neutrino oscillations. I will just give a brief introduction of how we understand neutrino oscillations. So we have a source of neutrino in this position X, the target or the detector of neutrinos in this position Y, and the distance of these 2 points is L, and it should be macroscopic. You will see in a second why it has to be microscopic for the oscillation to occur. And then we have some source of neutrinos. So here I'm giving an example of pion, but could be any other thing that produces neutrinos. So the pion decays. I'm putting this arrow because it could be anything, but pion just produces a lepton and a neutrino. And then this reaction produces the lepton that we call the alpha lepton, so that's why we identify neutrinos as alpha in the production, and then we associate a matrix element for the production. And then, of course, we have the propagator of the neutrino. So we understand the neutrino oscillations with a virtual neutrino here, and the neutrino that we put here is the mass neutrino, so that's why the propagator here with mi, and with this momentum of the neutrino. And we have the detection matrix element at this position here, and then we associate the neutrino as a beta neutrino because the reaction emits a beta neutrino here, or a beta lepton. And of course, this interaction, because this is mass in the mass basis, we have to add the mixing angles with alpha and beta flavors here. And of course, Feynman rules, we just integrate over x, we integrate over the momentum, and sum over all the possible mass states here. And we want the mass square total, so we square that. And after we square, if we have a very large distance, so we have to perform this integration, for example, with this exponential here. And there's a theorem that guarantees that this integration, if this L is very large, then the neutrinos will behave very closely to you would expect as if neutrinos were real particles. And then this will reduce to some oscillation phase here, which is proportional to the m square over the energy of the neutrino times the distance. And then when this happens, production, propagation, detection decouples, and then we can write it like this. We have the matrix element squared of the production, detection, and this factor here related to this, and the mixing matrix. And then after phase integration, we can write roughly the number of events as the flux of neutrinos, the oscillation probability of the neutrino from alpha to beta, and then the cross-section of the neutrinos. And this term in here, we identify as the oscillation probability. And since we are measuring the number of neutrino events, this means we are measuring the PMNS matrix. So we are measuring the N, so we can measure this component, this MI, and even the flux and cross-section, right? And we expect that in future neutrino oscillation experiments, the measurement of this mixing angle to be very precise, around 1%, even smaller depending on the angle. And we actually can use this precision to probe mass models. So I will show what a model has to have in order for us to probe the mass model of the neutrinos. So I took these two models, this warp flavor symmetry model given by this paper and the revamped A4. The details of how neutrinos masses are generated are not important for us. I just enumerate some important characteristics. And I want to emphasize that first, they add some flavor symmetry. So this one, A24 or A27, and this one, A4. And because of the symmetry, they reduce the number of free parameters in the mass matrix of the neutrinos, and which means that the model predicts the three mixing angles and the phase from actually only 2 parameters. So that is a feature of both models. So from the 4 parameters is reduced to 2. So this adds correlation between all these parameters here, or all these parameters here. And adding correlation, this means that if we make a plot, for example, sine squared theta 2, 3 versus delta CP, the allowed region of the parameter is, for example, in this model, is this yellow region here. So not everything in the parameter space is allowed because of this correlation. Same thing for the other model, only this green band is allowed from the model. And because we are able to, in the future, observe very precisely what's the value of delta CP and theta 2, 3. For example, let's look at this. Imagine that the true value of nature is this star point here. The allowed region of this model will become much, much smaller than that initial part here. So we can really try to exclude the model depending on where you are in the parameter space. And this other plot here is a little bit different. It's assuming that the true value of the sine of theta 2, 3 and true value of delta CP lies in some region here, how much the model can accommodate the mixing matrix. So if we measure something around here, then we can exclude the model with future experiments. In this case, Dune and Dune here. So that's a way of restricting or probing neutrino mass models with oscillation experiments. But we can go beyond model dependent. We can go and check phenomenological consequences of neutrino oscillations. So remember, again, that the number of neutrino is proportional to the flux, probability of oscillation, and then cross-section. And many physics actually change all of these functions here. So I gave a small table with several physics scenario that changes, for example, flux, probability, and cross-section. And just for you to think about what kind of physics changes those things. For example, non-standard interactions. We can add, for example, a new interaction of neutrinos with quarks up and down with the gamma 5 here. And this will change, for example, the decay of the pion. And if it changes the decay of the pion, it will change the flux of neutrinos. We can also add steryon neutrinos. And this means that there is another channel for oscillation. So muon can now oscillate, for example, to steryon neutrinos. And of course, this will change the probability of oscillation. We can have neutrino decay. So if there is a very light particle here, for example, neutrino 2 is heavier than neutrino 1, then neutrino 2 will decay to neutrino 1. And if the decay is large enough, then it will change the number of neutrinos that we observe in the detector. We can even go some very different models, for example, Lorentz invariance violation. So we can modify the Hamiltonian propagation from this to something that violates Lorentz. And we can actually use neutrino oscillation to probe or test if this value is different from 0 or not. And now I will discuss more detail, a little bit more detail, the non-unitarity. So let's take as a case study to make it more realistic. And the question that you can think about is, can really a mixing matrix be non-unitary? It actually can if we think a little bit more about the physics. So for example, imagine that we have more than 3 neutrinos. Then the big mixing matrix n times n is unitary. But this small part 3 by 3 is non-unitary. And if the energy of the experiment is smaller than the mass of the neutrino, then the neutrino cannot be produced because it will violate energy conservation, for example. So we do not have access to these parts here in the oscillation probability, for example. And then only this part will appear in the oscillation probability. And this part is not necessary to be unitary because it's a smaller part from a total unitary matrix. And then we can, for example, separate this 3 by 3 by the usual PMNS matrix that's unitary by some deviation from unitary with these parameters. And some of these parameters can actually be complex. So for example, this alpha 2-1 can have a CP phase, and we showed that the CP phase can fake the signal of delta CP. So in principle, we could think that we are measuring delta CP. We are actually measuring a delta CP from another source, not the usual delta CP from PMNS matrix. But we want to go beyond and try to test unitarity of this mixing matrix model independently. So this is kind of model dependent, right? But how can we really test model independently? One way of testing is really measuring the sum of the square of these matrix elements. So the problem with that is that if we want to make this measurement, we have actually to measure all the oscillation parts. So muon to electron, muon to muon, and muon to tau. And the oscillation mu to tau is really hard to measure because you have to measure the tau, and tau is very massive, so you have to go energies beyond the mass of the tau. But the tau decay is also very fast. And if it decays very fast, then you cannot observe the tau, so you have to observe the decay products. And not every experiment can do that. But we show that the DUNE can observe the hadron decay because the resolution of the detector is good enough to observe the hadron decays and observe it and identify it as a tau. But of course, it's not going to be very precise. But we can use that to finally measure the degrees of non-unitarity of the mixing matrix. So this is just to show, so this sign of the angles here are related to this matrix elements squared. So the red curve is related to the muon to muon oscillation. We see that it's very precise measured in DUNE. Same thing for the muon to electron oscillation, very precise. And the tau measurement is not that precise, much larger than these two regions here. But even if it's not that precise, we can actually test the unitarity at around 5% at 1 sigma in the DUNE experiment. Any questions so far? Okay, so let me move to phenomenology of neutrinos outside of neutrino oscillations. And actually, there are two interesting phenomena that I want to discuss. The first one is neutrinos detected at dark matter experiments. And it's interesting that the goal of dark matter experiments is to actually detect dark matter, right? But can we really detect neutrinos and use that to probe neutrino physics? First, let's look at what the detector of dark matter looks like. It usually very large masses, so bigger than 500 kilograms, goes for a few tons, even could be more. It is optimized for large masses particles, which large means large compared to neutrino standards, which are very small. But it can observe electron recoil and nuclear recoil. It has very low detection threshold. And usually the targets have a lot of nucleons or electrons, which is something positive also to consider. So the mass for comparing to neutrino experiments not that large. There are neutrino experiments with kilotons, megatons. The optimization is not very good for neutrino masses, but being able to observe electron recoil is good. Having low threshold is also good. And also, of course, many targets for detection is also good. So which neutrinos we can observe in dark matter experiments? Actually, we have to think about what kind of neutrino interactions will occur. So neutrinos can interact with electrons in xenon. And if you check the xenon orbitals, you'll see that the energy of the xenon orbitals goes from 12 eV to around 30 keV. So any neutrino with energy larger than 12 electron volt will produce some recoil energy. And there are many neutrinos. I mentioned in the beginning, solar neutrinos are produced and arrive at the detector, and this is a flux of neutrinos versus the energy. And we can see that this is the PP cycle, have a lot of neutrinos around the 400 keV, or a little bit below that. So there are a lot of neutrinos arriving at the detector with enough energy to remove an electron from the xenon orbital. And then if there are neutrinos colliding with the detectors, have we detected these solar neutrinos in dark matter experiments? The answer is probably yes. Unfortunately, the background is very large, so we could not see them. This is a plot from the Xenon 1-ton experiment. And then the red curve here is the total background. And we can see the solar neutrino predicted by the Xenon 1-ton is this brown curve here. And we can see it's many orders of magnitude different from the total background. But fortunately, future experiments, for example, Darwin, this is a spectrum from Darwin, and they changed the color for the PP to this green curve. But there's a very tiny region here. It's tiny compared to the whole energy range, but it's not that tiny if you zoom in, and we have precision to zoom in here. That neutrino background will dominate. So this means that we can observe neutrino from the sun in dark matter experiments in the future, most likely. So how this interaction occurs and how we can use that to probe new physics, for example. So let me just give you a brief explanation of how the weak current generates these events. So we have the cross-section of the neutrino colliding to electron and producing an electron with TR recoil energy. And this is what the cross-section looks like if you calculate from diagrams like this, so Z or W, for example. And then we have the propagator of the Z. If the momentum transfer is small, which is compared to the mass of the Z boson, then we get this Fermi constants here in front. And we have some dependence on the recoil energy over energy of the neutrino, which is very small at the region that we have access. So this is mostly flat. So that's why the event numbers of neutrinos is flat that I showed before. But we can modify this with new physics. So for example, instead of using the Z, we could use some scalar particle here. And scalar, in this case, I'm putting some scalar couplings and also some pseudoscalar couplings. And we can also, instead of having just an electron neutrino here to an electron neutrino, we could put some sterile neutrino with some mass here. So it changed the cross-section a lot. So this is the kind of Lagrangian that I'm talking about. So neutrino, some coupling here, and some coupling to electron. And let me just give a look at why this works for this kind of neutrino. So this is the cross-section plot versus the recoil energy of the electron. And if we go put this ms, m5 to 0, then there will be this TR here. And for the scalar particle, this TR is going to be very small. So we have this ME. So the behavior is 1 over TR. That's why the blue curve has this peak at low energy. The standard model is flat, so this red curve here. And then the pseudoscalar, because of this TR and this TR, it is going to be flat like the standard model. But if we put, for example, this mass to non-zero, around, for example, 8 keV, then we have this ms divided by this TR, for example, and then we can have some improvement, increase in the cross-section of the, at the lower end of the recoil energy here. And notice that the size of this coupling constant is very small, 10 to the minus 3. So we could have very large enhancement at this low threshold regime here. Of course, in practice, a little bit more complicated because the mass of the mediator has to be larger than 0 from other bounds that I haven't talked about. So it decreases a little bit the cross-section for the pseudo-scalar and a little bit for the scalar interactions. And actually, the situation is a little bit more complicated that we showed in this paper here, that because the binding energy of the electron in the xenon atom is around 10 to a few keV, actually, if the cross-section is not exactly as the free cross-section, it has some the distribution of momentum and energy of the electron will change a little bit the cross-section, and it can be important for this recoil energy at this site. So, for example, if the electron is deeper and deeper, it will become more different from the free cross-section, and if we go to electrons that are more outside of the atom, it gets closer and closer to the free cross-section. But if we consider everything, then we can give, for example, some prediction of the bounds for future experiments, and then we can see that depending on the mass of the sterile neutrino, we can get some very strong bounds, for example, around 10 to the minus 14 to the 10 to the minus 13 constraint here. And this is the last topic that I'm going to talk about.
So, Pedro, just a question, a naive question. So, is there any chance that sterile neutrinos can close the universe? Can be the whole dark matter, or just part of it?
It really depends on the model.
Okay.
Yeah. And depends on how you define sterile neutrinos. Is this just a neutral fermion, or does it have to mix with neutrinos and have some oscillation? So it depends on how you define, but yeah, it could. Okay.
I have a question. Even for standard model neutrinos,
Uh-huh.
you have this problem that it's a problem for dark matter detection because you're reaching what is called the neutrino fog or neutrino floor. So my question is, suppose if there is an event or an event, can you distinguish if it's a neutrino or something else in the standard model case?
I think it's not that easy to distinguish. I don't think I cannot think of a way right now of distinguishing. Yeah, I don't think it's very easy.
Question.
Yes. So when you're looking for dark matter, you put bounds on the parameter space of cross-section and the mass of the dark matter. But there is a line there, which is called the neutrino floor or neutrino fog, which are events that are not produced by dark matter, but by standard model neutrinos. And that's a limitation on finding dark matter. So it's a problem. If you are there, it's a problem because you find neutrinos, but it may be masquerading the dark matter. So my question was, if you find an event there, can you distinguish between a neutrino-induced event from something else?
I see.
And I think the answer is no, and that's why it's called neutrino fog.
Yeah.
Unless you have directionality, which in this most of the detectors you don't.
Yeah.
But there's some research now trying to build dark matter detectors that are sensitive to the direction. So you can analyze the recoil, and because some of this or most of this comes from the sun. So there is a way, in that case, there is a way to distinguish between a neutrino-induced event and something that's a dark matter event that you don't expect will come from the sun.
Okay, yeah, thank you. So, yeah, before I continue, I just want to discuss that when I started working with neutrinos, so neutrinos 94 years, I have been working with neutrinos for the past 10 years, roughly. And I began thinking about that everything was done on neutrinos, and there was nothing else to be done. And I soon realized that that was not true. There are many things new to be searched in neutrino physics, fortunately, because we have many things to discover in the future. And I'm going to talk about this very new proposal of atomic transitions. But there are things, even in the standard scenario of neutrinos, that we haven't even detected yet. So if you are curious, for example, you can check these two papers, but there are more things in neutrinos, even standard scenarios that we haven't measured yet. But let me go to these atomic transitions using neutrinos. So there's this very recent idea, so 2007, where Yoshimura proposed this neutrino pair emission from excited atoms. And what is this pair emission? So if you get some excited atoms and you are clever in how you excite these atoms, and then these atoms transitions to a ground state, it can emit some photon and a neutrino pair. The Feynman diagram looks like this, so electron coupled to the atom, and then it will have the Z and produce a neutrino pair and a photon, or something like this with a W. And this process has many advantages, but a few disadvantages that I will talk.
Or is the electron
No, it's the electron inside of the atom. Yeah.
Sorry, Pedro, are you looking for new physics with this, or this is something you have already seen and you want to explain with neutrino physics?
No, we haven't seen that yet.
You haven't?
Yeah. So it will have some standard model events, and I will discuss how we can also use that for new physics.
Okay.
But it haven't been measured yet.
Okay.
Yeah. So what's the advantage of looking into this? First, atomic transitions, very small energy. Or 1 eV, even smaller than that, which is very close to the neutrino mass. So it's easier to be sensitive to the neutrino mass. We can actually measure the emitted photon. I will show why this is important, but we are very good at measuring photons. This process, because of the photon, can be stimulated and coherent enhanced, so we can make a lot of events, even if it's suppressed from the weak interaction coupling constant. And it's interesting because this is a small energy, so it would be nice to test neutrino physics in a very different energy regime. But of course, there are some difficulties. For example, we cannot measure neutrino. The flux is small. The energy of the neutrino is also small, so it's very hard. There are some backgrounds that we still don't know how to remove. So for example, 3 gammas background is still a problem. People are working on that. It is experimentally challenging to maintain the coherence of this process. People are still looking into that, so there are a few technological advancements that has to be accomplished before we can do this kind of experiment. And since this is very new, there is still theoretical investigation, even in the standard case, that it still needs to be done. But if we can surpass these difficulties, the benefits are great, and I will show some of the benefits that we can extract from this. But let me explain what is this radiative emission of neutrino pair and why I call it neutrino laser. It will be clear why I call it like that. But before I go, let me explain how a usual laser beam works. So you put some atoms in some excited states, metastable state. You have the ground state, and then you put some laser to stimulate this transition. And then when the electron transitions from one state to the other state, it will emit a photon with the same phase, same momentum, same direction of the stimulated laser beam. And we call this a E1 or M1 transition, depending on what of the couplings between the electron and the atom that allows for this transition to occur. The radiative emission of neutrino pair, which we call ramp, is very similar to that. So we have excited state, we have a ground state. Of course, we have to forbid this E1 and M1 transition to occur, or else it will occur and emit just a photon. So if it cannot occur at first order, then we have to have some virtual state, and the virtual state has larger energy so that this transition cannot occur naturally. And then you put 2 laser beams instead of 1 to stimulate, make the coherence of the volume of target atoms that we are stimulating. And when you stimulate, it will make this transition through this virtual state. And when it transitions, one of these transitions will emit a photon, and the other one can emit a neutrino pair. this is called E1 times M1 transition because it's second order. So for example, M1 here, E1 transition here. And the important thing is that we emit neutrinos, so we have access to neutrino physics. And we also have the photon, so we can measure this photon and extract information from the neutrino physics. And one thing that I want to mention is that very, very recently, 2019, people have been able to do the measurement for gamma, two photons instead of neutrino pair. So neutrino pair, one photon. So their process is very similar to that. They were trying to show that it is possible to do that with gamma because it's the first step in order to arrive at the neutrino pair emission. And they were able to measure that. So how to extract neutrino physics from that? First, so we are measuring the photon, and the photon will contain information of the neutrino physics and of the neutrino pair. In order to see that, because of we first look at the frequency of the photon that's being emitted, and the frequency is fixed by the stimulated laser. So the laser has some fixed frequency, and then the photon that's emitted has this frequency of the stimulated laser. And what we have is that the number of photons that is emitted, the number of stimulated emissions will depend on this frequency here. And we have two information that we can extract. One is called the spectral function, which is this I of omega, and we have these thresholds of the reaction. So if the frequency is larger than this value here, then the reaction cannot occur. And actually, there are information of neutrino physics from these two parts here. So actually, people call the thresholds as the smoking gun, and you see why. So from conservation of energy, the energy difference between the excited and ground state has to be the sum of the energy of the photon plus the energy of the neutrino pair. If the neutrinos have no mass, then at the maximum frequency of the laser occurs when the invariant mass of the neutrino pair is also 0. So the two energies are divided equally from the photon and the neutrino pair, which is that delta E over 2. But if neutrino have mass, the neutrino pair cannot have a 0 invariant mass, and this maximum frequency is a little bit smaller than the delta E over 2. And the quantity, the thing that is smaller is related to neutrino mass. So you can effectively measure neutrino mass if you can measure the threshold frequencies of this reaction. And of course, we have 6 thresholds because we have 6 combinations of neutrino masses in the standard model. So this is what it looks like, the spectral function, which is related to number of photons that you can observe. And if the neutrinos have 0 mass, there is only one threshold, which is this delta E over 2, which is around here. So it's almost flat. But if we have energy frequencies, then you can put, for example, a laser beam around here, and then measure the number of photons, and then you can change the frequency, and you see a jump, and then you can effectively measure the threshold. And the threshold will give the mass scale of the neutrino, because you are actually measuring the mass of the neutrino. And the number of events actually give you the ordering, for example. So normal ordering, inverted ordering will give different sizes of events here. So you can actually measure the mass hierarchy. And this paper showed that under reasonable experimental assumptions, if it's possible to do this experiment, you can actually measure at 3 sigma neutrino mass scale and mass ordering. So we saw that idea, and we thought, maybe we can do some beyond standard model physics with that. So for example, go back to that Feynman diagram. Instead of the Z, we can put some new mediators here. And why this is interesting for new mediators? So let's take a look at the propagator of the mediator. So momentum transfer minus the mass of the mediator here. For the standard model, this is the W mass is much larger, so this is suppressed by the mass of the W. But if this Z prime and phi is not that massive, then we have a line mediator, and for example, we could even reach 1 over Q squared. And then we have an enhancement of the new physics process compared to the standard model process by even 10 to the 21 orders of magnitude if the momentum transfer is around this 1 EV scale. So that means that we can probe very tiny couplings of these mediators with electron and the neutrinos. And we show that that is actually true. So for example, red giants and other stellar objects can constrain this kind of couplings of neutrinos and electrons from the cooling of the stars, or for example, BBN, non-standard interactions, and there are regions of the parameter space that this kind of experiment can win over these constraints here. And one other thing that I want to mention is that actually, so it's very good for light mediators. So if the mediator mass is very small, then you have a very good enhancement. And the standard model has a light mediator, which is the light. And that's actually, it's so light that it's massless. And neutrino, even at the time that Pauli proposed this, he said that neutrinos could have a magnetic dipole moment. And if it has a magnetic dipole moment, it can connect to a photon. And then you can think, can a neutrino really interact with a photon? It's well known that neutrino charge is 0 or very small. But surprisingly, even with a 0 charge, you can interact with photon, even in the standard model. So this is a general interaction of neutrino with a photon. So the photon, neutrino spinors, and then the vertex function here. So the vertex function can be written in terms of these functions here. So FQ, FA with a gamma 5, FM, and FE. And at zero momentum transfer, we understand these functions here as the charge of the neutrino, the anapole, the magnetic moment of the neutrino, and the electric dipole of the neutrino. Actually, since the charge is too small, we usually go to the next order expansion and define this charge radius. So if you want to see more, check this paper here. But actually, the standard model even predicts that these quantities, all of these, are non-zero. Yes. Uh-huh.
You mean it is smaller than 1/3 or 2/3 of the quark masses? Is
No,
infinitesimal?
No, it should be really, really small. I don't remember.
It's a fractional number. You mean is something?
Yeah, it's like 10 to the minus 10, for example. I don't remember the exact number, but it's very small. If it is non-zero, it has to be very small from some constraints, for example, neutrality of the matter in the universe, for example. So it has to, if it is non-zero, it has to be very small. So that's why I take it as equal to 0 in calculations. Yeah, so if you check the standard model, it will have some loop that can generate this kind of interaction. For example, W, neutrino, neutrino, and charged leptons, or neutrino, charged lepton, WW. Of course, this is suppressed by the W mass, but if you do the calculation, you see that the magnetic moment of the neutrino and the electric dipole is 10 to the minus 19 Bohr magneton, and the charge radius and anapole 10 to the minus 33 centimeters squared. So in principle, it can interact with a photon in some way, and we have some bounds on that already. So the current bound on magnetic moment is 10 to the minus 12, so very different here, 7 orders of magnitude. But surprisingly, the charge radius and anapole is actually 1 order of magnitude, roughly, difference. So maybe in the future we can actually see that in some, this comes from scattering experiments. So actually, and a fun fact is, if neutrinos interact with photon, then neutrinos can decay. The standard model predicts that neutrinos can decay. And of course, if you do the calculation in the standard model, you get that the lifetime of the neutrino is much larger than the age of the universe. But in principle, neutrinos can decay even in the standard model. What do you mean same? I'm not sure if I understand the question. Maybe you'll give. Yeah, no, it's the same order of magnitude, not exactly the same value. Yeah.
I'm late.
Yeah, I think, yeah.
Oh yeah, I just asked about these 4 different moments.
Yeah.
Why are there 2 predictions for them? And apparently the predictions are slightly different, but...
Yeah, could be different, but they are roughly the same order, yeah.
Thanks.
Yeah, don't take this value exactly like that, yeah. So how we constrain this kind of magnetic moment, electric dipole, charge radius? We use scattering experiments, for example. So the cross-section between neutrino and electron, giving some neutrino and electron, looks like this. So magnetic moment here. Charge radius, also cross-section, neutrino, electron, neutrino, electron. If you do the calculation of the cross-section, you have the charge radius here. And actually, magnetic moment charge radius is effective. Notice the effective part. I will show how they look like in a second. Same thing, we can check for neutrino decay, even if it takes really, really long. If you have a lot of neutrinos, some of them will decay. And if you calculate the decay, also effective magnetic moment here. Stellar cooling, also the plasmon, also the gamma in the star can have an effective mass, and then this can generate neutrino gammas into neutrinos. Again, effective magnetic moment. Notice the effective. And if I write down what the effective means, you see that it has mixing matrix, a combination of muon, epsilon, a combination of charge radius, anapole, mixing, combination. It always appears as a combination of things. And since it's always a combination, it happened that some cancellation occurs, and we are missing possible observations because one thing cancels to the other, and then even if this M is non-zero, this can be 0, and then we cannot observe that. How about radiative emission of neutrino pair? It has some advantage. So let me just show how it looks like. Instead of this Z prime and phi, we put a photon here. And then this is good because photon is a light mediator, so we have good sensitivity. And because we can check the trigger laser frequency, we actually don't have a combination of matrix elements from each interaction. So let me show what it would look like. So the black curve here is the standard model. So suppose we have some magnetic moment around here, just to illustrate. And then if I activate just the 1, 2, then the curve looks like this. It for example, becomes non-zero around that area. So if we see some non-zero here, we know that, for example, it's not the 3, 3 that's generating this non-zero excess here. So we can really tell that it comes from mu and not from mu 1, 2 and not from mu 3, 3, for example. So we can really disentangle the element of the magnetic moment that is generating this excess if we can observe that. And actually, we can go even beyond that if we plot the shapes of the curves. So for example, I plot here the component 1, 2 as a non-zero quantity. And we can see that the curves are very different. So for example, blue to black is very different. And the green to red, it does not look different here. But if I extend this further, it will look more different. And we can really see that we can not only tell that the element 1, 2 is the one that's non-zero, but it's, for example, it's the muon and not the epsilon that's non-zero. Actually, we did the calculation carefully, for example, and check for one experimental configuration and put the magnetic moment, magnetic moment true as 10 to the minus 11. So we can really see that it gets a minimum at minus 4 and 4, which is expected because we are sensitive only on the absolute value squared. But if we compare with the curve, for example, with the electric dipole, we see that it doesn't reach 0, so we can exclude around 4 sigma, that it really is the magnetic moment and not the other quantities here that are generating this excess. So this experiment is very special in this sense because it can really distinguish what is the what is the form factor of the neutrino that is generating this kind of excess, if we observe, of course. So let me just finish my talk here with a takeaway and final thoughts. Neutrinos are one of the main topics in particle physics in the past, today, and in the future too. Next decades, many neutrino oscillation experiments and dark matter experiments will release important data, and maybe there's new physics, or at least some exciting news from the data will appear, so stay tuned on that. If you have a model that explains neutrino mass, and you should because neutrino mass is different from 0, you can test it most likely in some way with new interactions, non-unitarity, or even if there's some correlation in your parameters predicted by your model. And there are many opportunities surrounding neutrino physics, oscillation, scattering, atoms. There are many more. And these opportunities are even related to standard physics of the neutrinos. And last, there are many things that has to be done for neutrino physics in the next 10 years. So I invite you to look at neutrino physics at some point. And that's all. I put many places that supported me over the years. So thank you.
Thank you. Questions? I have a question, actually. You said that neutrinos can decay according to the standard model because of loops, right? but the lifetime would be larger than the age of the universe.
Right.
Very interesting, but I wonder how this scenario could change if you take into account that in the early universe, the temperature is very, very large because you have stimulated emission of photons. So this could make neutrinos to decay much, much, much faster.
Why it would decay faster?
Because of stimulated emission.
Ah, okay, see.
Do you know anything about this? Have you seen any calculation?
No, I haven't. But
Okay.
I see what you mean, yeah. I don't know. I don't know how it would look like.
Okay.
But I guess it would be in thermal equilibrium, right, everything?
What?
It would be in thermal equilibrium, right?
What would be in thermal equilibrium?
The whole universe.
Yeah, but neutrinos would decay faster because of this.
Right,
Because of
but
the
then there were other interactions that will equilibrate, right?
It depends.
Yeah.
It will depend on the coupling, right? Because the decay is very slow. So, I don't know.
Right, yeah.
Yeah, it may be if it's in thermal equilibrium, but because, I don't know.
Right.
Yeah, that's what I mean. And because it's a loop calculation.
So I have
Yeah.
a question. So there are experiments looking for coherent neutrino scattering that
Right.
was detected recently, and also in Brazil there's one called CONI.
Right.
Is there any advantage in looking for beyond standard model with looking at coherent neutrino scattering?
Of course, yeah. For example, NSI, you can try to test on this kind of experiment. I don't have a plot here, but it can put some important constraints. Even in
what
the
is NSI? Sorry, neutrino?
non-standard interactions. sorry.
Non-standard
So
interactions,
non-standard interactions. And I didn't put here, but some of the bounds from the magnetic moment also comes from the coherent scattering. So you can also put bounds on this. But it's also a different combination from that one, but it's also a combination. So you could also constrain this kind of coupling.
Okay, thanks.
I didn't understand how you measure the ordering of the mass, and if you can also measure the absolute mass of the neutrinos.
Can you say that again?
I didn't understand how you measure the ordering of the masses, and if you can also measure the absolute mass.
So yeah, the ordering is a little bit tricky because the oscillation probability, I'm not sure let me see if I can go back like this. I think I passed the. Maybe I write in the board here. So I showed the oscillation probability, something like that, right? Sine theta squared, sine squared, tell that m squared over 2e L. So if we change the sign of that, because this square doesn't change anything, right? So if the oscillation probability looks only like that, then you cannot measure. You can only measure the absolute value. So that's what happens with delta M31. So that's why we only measure delta M31 absolute value, because the leading term of the oscillation probability that we observed with experiments looks like that. So future experiments will be able to measure other terms. So this is for 2 neutrinos. We have actually 3 neutrinos. We have matter effect. So there are some other terms here that depends on the sign of that. So for example, the solar neutrinos have a very strong matter effect, and then this will change a little bit, and then you are sensitive to the sign of that, and then you can tell. So that's why delta M321, we know that 2 is heavier than 1. So in the future oscillational experiments, because of the matter effect and the sensitivity to the other terms, we will be able to measure the ordering. So that's how you measure the ordering, and that's why we don't know yet. But it's always a difference in mass. So the mass scale is really hard to measure. So for example, you can try to measure the neutrino mass using beta decay, which is the when neutrinos were proposed. If you can, so the beta decay looks like this, right? Something like that. And so if it's a two-body decay, the maximum energy of the electron is going to be exactly the energy expected by the two-body decay. And there's a very tiny gap here that is very hard to draw. And this tiny gap is related to the neutrino mass, because part of the energy of the reaction goes to the neutrino mass. So if you have an experiment that's really, really precise, you can try to measure this gap here. And some experiment, I think one of the experiments that I put in the beginning slide is the Catering experiment. That's exactly like that. So it can, in principle, measure this gap and then measure the neutrino mass. So this is one way of measuring. There are other ways. For example, cosmology. Neutrinos have an effect if neutrinos have mass. And actually, Catering experiment probably will reach sensitivity around mass of the neutrino. Actually, it's the combination of the neutrino that's related to the electron. Around, I think it's like 0.1 or 0.2, something like that, EV. So actually, the cosmology bounds are already better than what Catering will probably be. But future cosmological observations will be able to probably measure neutrino mass because they will be sensitive to neutrino mass. So most likely cosmology will be able to measure neutrino mass.
And do you know what are the time scales for getting this measurement from a direct experiment?
The time scale of what?
To get this measurement, like in 10 years?
Yeah, probably 5 to 10 years, yeah. Well, for Catering, 5 to 10 years. Cosmology, I think DES is already running. I think you probably know better, right?
Yes. I know the cosmology side. Already last week we had DAISY BAO measurement, and they claim that they have like upper bound of the sum of the neutrino mass that is below the inverted ordering at 95%, but it's still debatable because their data has some points that people don't understand really what it is. But in 10 years, cosmology will have, probably.
I hope to be still here. Other questions? No? So we thank again Pedro for his talk. And there are cookies upstairs.